5 math results your brain will refuse to believe. You already know some of them, you will still get them wrong. Number 5. 0.999 repeating forever. Most people will tell you it's just below 1, almost 1, practically 1. They're wrong. It isn't close to 1, it isn't almost 1. It is exactly, precisely, provably equal to 1, the same number. And this single fact has started more arguments online than almost any other in math. So let me show you 3 different proofs, and then you can go fight about it in the comments. Here's why your brain hates this. You picture a number line, there's 1 sitting right there. And just a tiny step to the left, you imagine 0.999, creeping toward it but never quite arriving. There must be a gap, right? Some impossibly small sliver between them. That picture feels obvious, and that picture is the lie, because that gap doesn't exist. Proof 1, the simplest one. You already agree that 1/3 equals 0.333 repeating. No argument there, it's basic division. Now multiply both sides by 3. 3 times 1/3 is 1, and 3 times 0.333 is 0.999. So if the left side equals 1, the right side must too. Same equation, both ends. 0.999 equals 1. Don't like fractions? Proof 2, pure algebra. Let x equal 0.999 repeating. Multiply both sides by 10. Now 10x equals 9.999, the same endless 9s after the point. Subtract the first equation from the second. On the left, 10x minus x is 9x. On the right, the infinite 9s cancel perfectly, leaving exactly 9. So 9x equals 9. Divide by 9. X equals 1. But we said x was 0.999. They're the same number. Still resisting? Proof 3. If 2 numbers are different, you can always find the gap between them. Subtract 1 from the other. So subtract 0.999 from 1. You get 0.000, and you keep waiting for a 1 to show up at the end. But there is no end. The 9s go forever, so the zeros go forever. The gap isn't tiny. The gap is 0. And 2 numbers with 0 distance between them are the same number. Number 4, a shape you can fill with paint, but never paint. This is a trumpet that goes on forever. It starts wide, and it narrows, and it keeps narrowing, stretching out to infinity and never ending. It's called Gabriel's horn, and it hides a contradiction that took mathematicians centuries to make peace with. This horn has a finite volume. You could fill it with a measured amount of liquid, but its surface, the skin of the horn, has infinite area. Finite on the inside, infinite on the outside, the same single object. Let me show you how that's even possible. Building it is surprisingly simple. Start with one of the most basic curves in math, y equals 1 over x. As x grows, the curve drops toward 0, getting closer and closer to the axis but never touching it. Now take that curve from x equals 1 onward and spin it around the horizontal axis. As it rotates, it sweeps out a smooth, hollow shape, wide at the mouth, tapering into an endlessly thin tail. That shape is Gabriel's horn. First, the volume. How much space is inside the horn? Using calculus, you add up infinitely many tiny disks along its length. The math gives a clean, finite answer. The volume is exactly pi. Not approximately, exactly pi. So even though the horn is infinitely long, the space inside it is limited. You could pour in pi cubic units of water, and it would fill the entire thing, all the way to infinity. Now, the surface area. You'd think if the volume is finite, the surface should be too. It isn't. When you set up the integral for the outer surface, It behaves like adding up 1 over x forever, and that sum has no limit. It grows without end. The surface area of Gabriel's horn is infinite. So we have a single shape with a finite volume and an infinite surface wrapped around it. And here's the part that breaks people. Since the volume is just pi, you could fill the whole horn with pi units of paint, completely full. But the inner surface of that same horn is infinite. So that paint, enough to fill the entire shape, could never be spread thin enough to coat the inside walls. You can fill it, you cannot paint it. The paint that fills it touches every part of the surface and still isn't enough to cover it. Finite and infinite, arguing inside one object that you could, in theory, hold in your hands. Number 3. The same data can prove two opposite things. 2 treatments for kidney stones, A and B. Doctors compared them on real patients, and here's what they found. For small stones, treatment A had a higher success rate than B. For large stones, treatment A again had a higher success rate than B. So A wins for small stones, A wins for large stones. There are only 2 kinds of stone. So treatment A is better. That conclusion feels airtight. It's also wrong, because when you put all the patients together, treatment B comes out ahead. The same numbers, saying the opposite thing. Let's look at the actual results. Start with small stones. Treatment A succeeded in 93% of cases. Treatment B, 87%. A is clearly better. Now the large stones, the harder cases. Treatment A succeeded 73% of the time. Treatment B, 69%. A is better here too. So in both groups, every patient type we have, treatment A has the higher success rate. By any normal reading, A is the better treatment. Remember that. Now let's do the obvious thing and combine everyone into one big number, the overall success rate. Treatment A, across all its patients, succeeded 78% of the time. Treatment B, overall, succeeded 83% of the time. Look at that. Treatment B is now winning. The treatment that lost in small stones and lost in large stones wins when you add the groups together. Nothing in the data changed. We just stopped separating the cases and the answer flipped. So what happened? The answer is a hidden variable the averages were hiding. Look at who got which treatment. Treatment A was mostly given to the large stone patients, the difficult cases. Treatment B was mostly given to the small stone patients, the easy ones. So treatment A's overall score is dragged down, not because it's worse, but because it was doing the hard jobs. B looks better overall, mainly because it got the easy patients. The size of each group and who landed in it is the lever quietly flipping the result. This is the danger of a single average number. An overall statistic can point in the exact opposite direction of every group inside it. And this isn't a one-off curiosity. It has shown up in real medical trials, in university admissions accused of bias, in studies of which jobs pay more. Whenever you see one headline percentage, the honest question is always, what groups got blended together to make it, and who decided how? Because the average can be true and still lie. Number 2, a tiny rounding error that broke the weather forever. In 1961, a meteorologist named Edward Lorenz was running an early computer simulation of the weather. To save time, he restarted one of the runs halfway through by typing in the numbers from a printout. But the printout was rounded. It showed 3 decimal places where the computer had been using 6. A change out in the 4th decimal, a difference smaller than a puff of air. And the forecast that came out the other side was completely, utterly different. Lorenz had just stumbled onto the reason we cannot predict the weather, and he gave it a name, the butterfly effect. Here's what he did next. Lorenz stripped the weather down to its bare bones, just three simple equations, describing warm air rising and cooling. Three numbers, looping through three little rules, over and over and over. That's the whole thing. No randomness, completely deterministic, simple enough to scribble on a napkin. And then he just let it run and watched where those three numbers would go. So let's start two of these simulations almost identically, with a tiny nudge out in the fourth decimal, exactly like Lorenz's printout. For a while, they trace the very same path, right on top of each other. Then they start to peel apart, and then they're gone, wandering off in completely different directions with nothing in common anymore. That microscopic difference has exploded into total disagreement. This is why a 10-day weather forecast is basically a guess. In a chaotic system, to see far into the future, you'd have to know the present with impossible precision. The flap of a butterfly's wings really could tip next month's storm. But now comes the part that is genuinely beautiful. Take that endlessly wandering path and plot it out in 3 dimensions. It never repeats. It never crosses itself. It never settles down. And yet somehow, it never escapes. It stays trapped, forever, looping around inside this one shape. 2 great spirals, joined in the middle, like the wings of a butterfly. Mathematicians call it a strange attractor. The motion is pure chaos, but the chaos has a form. And that's the twist that closes out all of this chaos. The exact path is unpredictable. We can never say which wing it's on at a given instant or when it's going to jump across. But it is always, without fail, somewhere on those wings. So chaos, it turns out, isn't the absence of order. It's a deeper, stranger kind of order. Unpredictable in every detail, and yet completely bound to a shape. We can't tell you where the weather is going, but we can show you the surface it's dancing on. And number 1, the party bet that fools everyone, including math teachers. What are the chances that 2 of them share a birthday? Your gut says, tiny, maybe 5%. The real answer is 50%. A coin flip, and with 70 people, 99.9%, your brain is screaming that this is wrong. Let me show you why your brain is the one that's wrong. Here's what your brain just did. There are 365 days in a year. So you imagine yourself walking into that room, comparing your birthday against 22 other people. 22 chances out of 365. That's about 6%. Feels right? And it is right for that for that question. But that was never the question. Nobody asked about your birthday. Question was whether any 2 people match, and that changes everything. Watch what happens when we connect every person to every other person. Person 1 compares with 22 people. Person 2 adds 21 more. Person 3 adds 20. Keep going, and 23 people create 253 pairs. 253. Each pair is its own little lottery ticket, its own separate chance of a match. You weren't playing one lottery with 22 tickets. The room is playing 253 lotteries at the same time. That's the trick your intuition missed. So how do we actually calculate it? Here's the elegant part. We flip the question. Instead of asking, what's the chance of a match? Ask, what's the chance of no match at all? The first person picks any day. The second person must avoid one day, 364 out of 365. Third must avoid 2 days, fourth, 3, guai. Multiply all 23 of those together. And the probability that nobody matches collapses to just 49.3%, which means the chance of at least one match is 50.7. It's all. Coin flip is real. And here's the curve that breaks everyone. The probability doesn't grow in a straight line. It explodes. 23 people, 50%. 50 people, 97. 70 people, 99.9. Think about your school classroom, about 25 kids, That's why someone always shared a birthday, when each I saw. It was never a coincidence, it was math hiding in plain sight. 5 paradoxes, 5 wins for math. Your brain fought hard. If you want a rematch, we drop one paradox every single day. Subscribe and bring your gut next time.